This is where we left off last week. We were talking about pancakes and limiting reactants. The question here was if we had this much flour, eggs, and baking powder, how many pancakes could we make? And we decided that we could make only 15 pancakes because at that point we'd run out of flour. We decided that limiting reactant is the flour. That's the ingredient that limits how much we can make. And the theoretical yield is the amount you can make using up all of that limiting reactant. So suppose we cook our pancakes and we accidentally burn 3 of them and 1 falls on the floor. Can you imagine that happening? Yeah, it could happen. So we had enough flour to make 15 pancakes, but we actually only end up with 11 pancakes because life happened, and life happens a lot. So if this was a chemical reaction, we would say that 11 pancakes is our actual yield. In theory, we could make 15, but we actually made 11 because some stuff happened that we weren't planning on. So the actual yield is the amount that is actually produced. The theoretical yield is the amount you could produce in theory if everything goes perfectly. Does everything ever go perfectly? No. Not in my life. It doesn't. Stuff happens. Happens in chemistry too. Well, we like to quantify things, and so one of the things we do is calculate percentages. So the percent yield for this example is the actual yield of 11 pancakes divided by the theoretical yield, 15 pancakes, times 100, 73%. So we had a 73% yield. That's not too bad, but it's not great either. You know, like 95% would be a lot better. That means that 73% of what we attempted to make actually got made. The actual yield in a chemical reaction has to be determined experimentally. It's going to depend on the reaction conditions, and it can change. Just like when you make pancakes, it depends on the conditions, you know. If you've been up late the night before and there's a lot of chaos going on around you, you might make more mistakes and drop more pancakes or get distracted and burn more pancakes. Your percent yield would be lower. The only way you can find out what the percent yield is by actually doing it. So in a chemical reaction, you perform the reaction and then you measure how much you actually made. And there's a variety of things that can happen that will keep your yield from being 100%. Not all chemical reactions go to completion. You might have all the right stuff to make 5 grams of something, but it doesn't actually go all the way. That's a very common thing that happens. There are also experimental errors that happen when you are collecting your product, or even in the process of making it. You might spill some of the reaction liquid or something, and you can lose some product along the way. So generally, a percent yield, there's a typo. The actual yield is almost always less than 100%. The percent yield is almost always less than 100%. Yeah, typo. The percent yield will be less than 100% because you lose some or some doesn't get formed. Every once in a while, you'll see a percent yield that's over 100%. Can you actually make more product than is theoretically possible? No, you can't, because law of conservation of mass says you can't create something out of nothing. What happens when you have something that gives you a percent yield greater than 100% is you may have some contamination of some kind. If you're making a solid and the solid is wet when you weigh it, the mass of the water that's making it wet is going to be included in the mass of the product, and it's going to appear that you made more than you actually did. So your calculated percent yield will be greater than 100%, even though you made an error. Another thing that could happen is something could fall into your flask or onto your product that would contaminate it and increase the mass. When I was in college in lab, a fly actually flew over a crucible where someone was incinerating something, and the fly, of course, the heat killed it. It fell into the crucible with this poor guy's sample and burned up. You can't pick fly ashes out of the other ashes. It's just not possible. So the percent yield would be too high in that instance. So that's the sort of thing that can happen. So here's a good summary slide. The limiting reactant, sometimes called the limiting reagent, is the reactant that is completely consumed, the one that makes the least amount of product. The theoretical yield is the amount that can be made in theory. This is the amount we calculate based on the amount of limiting reactant. So this is calculated. Actual is measured experimentally. So in lecture, the actual yield always has to be given to you because we're not doing an experiment. So we'll give that to you. And then here's the equation for percent yield. The actual yield divided by the theoretical yield times 100. And again, we're using percent here as a unit. Do not use the percent button on your calculator when you multiply by 100%. It'll give you the wrong answer. So let's apply this to a chemical reaction, titanium and chlorine. So the question is, what are the limiting reactant and the theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So the strategy here is the first thing we need to do is we need to use stoichiometry to find the amount of product that can be made from each reactant. That's what we did with the pancakes. The limiting reactant is the one that gives us the smaller amount of product. And that smaller amount of product is the theoretical yield. Okay? So let's get rid of all those extra words and just get to the problem here. This is stoichiometry. We have a balanced chemical equation. We're going to use it to organize this information. 1.8 moles. So I'm going to write that under titanium. 1.8 moles. And 3.2 moles of chlorine. The question is the limiting reactant and the theoretical yield. So the theoretical yield would be the amount of product. I'm going to do it in moles. It doesn't say what unit it wants it in. It just wants the yield. And so we could choose. I'm going to choose the easy thing, moles. So what we need to do is two calculations, find out how much product we can make from 1.8 moles of titanium and how much product we can make from 3.2 moles of chlorine. So 1.8 moles of titanium. And the path that we learned last week was grams to moles to moles to grams. Okay, this one, we're starting in the middle. We're given moles, and we can end at moles. So we just cut the ends off. You have to do the middle, though. So we're going to go moles to moles. So moles of titanium to moles of the product, TiCl4. And I want to divide by moles of titanium so those units cancel out. Do you remember how we got the numbers for this ratio? Mole to mole ratio comes from where? The balanced chemical equation. So for 1 mole of titanium, I get 1 mole of product. There aren't any coefficients written there, but we understand that there's a 1 implied. So 1 and 1. Well, that math is pretty easy. That's going to come out to be 1.8 moles of titanium 4 chloride. That's not necessarily our answer, though. We also have to figure out how much product we could make from this many moles of chlorine. So we'll have another calculation, same kind. So chlorine, and now we're going to figure out how many moles of product we could make from that. So we want moles of titanium chloride on top and moles of chlorine on the bottom, so that the units cancel out. These are the sorts of calculations we did last week. What number do I put in the numerator here? 1. And what number goes in the denominator? 2. It takes 2 moles of chlorine to make 1 mole of titanium chloride. So this ends up being 3.2 times 1 divided by 2. 1.6. So 1.6 moles of titanium chloride. We now have 2 quantities of product. Which is the theoretical yield? The big one or the little one? The little one. The smaller one is our theoretical yield. So if you just have this work on a lab, you'll lose points because you haven't chosen an answer. The work is beautiful. I did it myself. It's beautiful. We need an answer, though, so we have to select an answer. For me, putting a box around it is choosing one, and that would be good enough on a lab. Nice touch to label that, though. That's the theoretical yield. So that's our theoretical yield. We can't make any more than that, because as we're going along and making half a mole and 1 mole and 1.5 moles, when we get to 1.6 moles of product, we run out of chlorine. Reaction stops. You're making pancakes, you run out of flour, you're done. You can't make pancakes without flour. Okay, so this is our theoretical yield, and we look back and see which reactant gave us the smallest number. That's the limiting reactant. We'll circle it down there, or circle it up here, and draw an arrow and call it LR, limiting reactant. Indicate to me somehow that you're choosing that as the limiting reactant. On an exam, you'll have to pick a letter, A, B, C, D, E. Any questions? Do you understand the process? It's like what we did with the pancakes. Figure out how many pancakes you can make with this amount of ingredients and that amount of ingredients and this amount of ingredients. The smallest is your answer. Let's do another one. So here's one. 4.8 moles of sodium and 2.6 moles of fluorine. What's the limiting reactant and theoretical yield of sodium fluoride in moles? Okay, so this is a better question because it's a little more specific. So we're going to do the same thing. 4.8 moles of sodium. I'm going to write that here, 4.8 moles of sodium. And we have 2.6 moles of fluorine. And the question is, how much of this can we make? We have 2 reactants. Even if they didn't mention what's the limiting reactant, if you see 2 reactant amounts, you're going to have to do 2 calculations. There are other ways to do it, but they are less straightforward. If you're comfortable with one of the other ways, you go right ahead, but I don't want to confuse everybody else. This is not the only way, but it's the way I'm choosing to show you. So I'm going to take 4.8 moles of sodium, and I'm going to figure out how much product I can make. Again, we're doing the middle of grams to moles to moles to grams. Just moles to moles. Moles of one thing to moles of another. So I want to find out how many moles of sodium fluoride. So I need to divide by moles of sodium. I look for these numbers in the equation. In front of NaF, I see the number 2. So I write that number here. In front of sodium is the number 2. And in front of sodium down here, I write the number 2. Well, you can see that the 2's cancel out. But if you do it on your calculator, you'll come up with the same answer. 4.8 moles of sodium fluoride. If we use up all the sodium, that's how much product we can make. Now we have to take the other reactant and do a similar calculation. It's 2.6 moles of fluorine. And again, we're going to multiply by moles of product and divide by moles of that reactant. I don't know what my iPad's up to. And again, for the mole-to-mole ratio, we look at the balanced chemical equation. In front of F2, there's no number. That's an implied 1. In front of NaF, there's still a 2. So 2.6 times 2 is, I believe, 5.2. 5.2 moles. So if we had enough sodium and used up all the fluorine, we could make 5.2 moles of product. How much can we actually make? It's the smaller one, the 4.8. Because when we get to 4.8 moles of sodium fluoride, we run out of sodium. We've used it all up. We can't do anything else. Do not take these two numbers and add them together. That is wrong. So this is our theoretical yield. Good grief. Theoretical yield. And what's our limiting reactant? Sodium. It's the sodium. The one that makes the smaller amount of product was sodium, and that's the limiting reactant. Yes?
How do you know that the limiting reactant is the sodium?
Well, I look at which answer I chose here, which was smaller, and then I go back and see what reactant did I start with there. Okay? So it was the sodium that gave me the smaller number. The fluorine gave me the larger number. Any other questions?